Thanks for the introduction. So, web security is a complicated topic, even for web security experts. In general, developing secure applications on the web is possible, but it's challenging. In particular, one of the reasons of this challenge is that the threat model we have to consider is quite complex, because we have to include both web attacks operated by some evil guys who control malicious websites, and network attacks were enabled by some attacker who controls all the HTTP traffic on the network. Indeed, this complexity is reflected into a number of different attacks, which one has to take into account when discussing web security, ranging from session hijacking to cross-site request forgery, SSL stripping. There are many attacks, which I'm not going to cover in detail here, but given this complexity and the difficulty in developing secure web application, a crucial point is that browsers are very natural candidates for security enforcement, because they're a centralized point where we can actually enforce security. And
so I was asking if you discussed this one. Okay.
Okay, so even if browsers are natural candidates for security enforcement, the baseline security policy, which is available in browser, which is called same origin policy, has a number of limitations. In particular, one of the main problems is that it is circumvented by content injection attacks. To exemplify content injection, I picked this simple snippet of PHP code. And the idea of content injection is that this attack happens when some untrusted input is treated as a markup element or code by our application. So in this specific case, for instance, we consider a page with a simple search engine. And what we do first is that we authenticate the user by calling session start. And then we read the parameter Q from the query parameters. And before doing the lookup, we print on the screen the value of this parameter, saying this is the results for the query term. What happens is that since the value of the search term is just taken from the attacker potentially and put inside the page, we expose the web application to an attack where an attacker who is able to craft this link is able to inject code into our web application. How can he do it? Basically, the idea is that we have to close this underline tag, and afterwards, rather than putting a search term, we actually put a script. And the point is that this script is not going to be printed on screen by the browser, like the search term, but it is actually going to be executed. So in this specific attack, by supplying this code, the attacker is able to read the cookie, which identifies the user session at the search engine, and exfiltrate the cookie value to the domain controlled by the attacker. And the point is that in this case, the attacker cannot be stopped because the script cannot be distinguished by other trusted scripts which run to the web page. Content security policy is a W3C standard which is designed to prevent attacks like the one which I presented, or at least to mitigate the impact of these attacks. And the core idea of content security policy is that we have a policy language which we can use to define restriction on content loading. And the idea is that the specification of the policy is done at the server side, but enforcement of the policy is instead done at the browser side. And the core strategy to prevent XSS, like the one I discussed in the previous slide, using the standard approach of CSP, consists of two steps. The first step is that we disallow the execution of inline scripts, which is the default choice of CSP, so that if the attacker is able to provide the script, like in the previous example, this script is not actually going to be executed by the browser. And of course, since you really want to use script into your own pages, the way you can load script is by fetching them from the external environment. And to constrain the origins from where the script can be loaded, you can use a whitelisting mechanism. To exemplify, let's pick this simple content security policy. In this policy, we say that scripts can only be loaded by the page by taking them from example.com using the HTTPS protocol. So the script must be loaded using an encrypted connection. And implicitly, we're also saying that no inline script is allowed to execute. Why is that? Because we are not using the unsafe inline keyword bound to the script source directive. So by default, inline scripts are blocked, as I mentioned. Also, what the policy is saying is that images can be loaded from the page from any web origin using any protocol, as represented by the wildcard star in the policy specification. And no other content types can be loaded by this page. So for instance, you cannot load the style sheet in this specific example. Previous research found some problems in the current CSP deployment. In particular, there are 3 problems which I think are particularly relevant. The first problem is that many websites use unsafe inline, most notably for backward compatibility reasons. Because removing inline scripts proved to be difficult in existing web applications. So developers just resort to activating unsafe inline in their policies, which largely voids the benefit of CSP. The other 2 points are trickier. One point is that whitelists are difficult to configure correctly. It is too easy to come up with whitelists which are either too strict or too large. And we say that a whitelist is too strict if it stops some legitimate functionality of the web application, while instead a whitelist is too large when it allows attacks. Because, for instance, it allows one to load scripts controlled by the attacker, or it provides access to JSON endpoints or something like this. And the last challenge which affects the current CSP deployment is that many websites, as of now, have a very dynamic nature, because, for instance, they include advertisement libraries, or they rely on contents which are relocated using HTTP redirects. And all these kind of behaviors are not easy to support by using static whitelist as advocated by CSP. In particular, we observed that during the years, CSP evolved to offer a robust solution to the first problem, because now CSP has mechanisms to whitelist individual inline scripts by using nonces and dashes, which are a very nice solution to the first issue. So you don't really need to refactor your web application to remove inline script, but you can just specify that only scripts with a given hash are allowed to load into your own page. Unfortunately, CSP does not yet provide some robust solution for the other 2 challenges which I present in this slide. So what we did in our paper, and I'm going to present briefly in this talk, is to propose an extension of CSP, which we call CCSP, which stands for Compositional CSP. And the core idea is that we are able to dynamically relax a given content security policy on our web page. And the strategy amounts to 3 steps. Initially, the page developer specifies some content security policy, which is a simple policy which only accounts for the direct dependencies of the pages, which are relatively easy to identify. And then, when the page interacts with other content providers, these content providers can relax the policy to load more stuff. So content providers are relaxing the policy, for instance, to support their own dependencies. And to keep control on this mechanism, page developers can put an upper bound on policy relaxation to have the final word on security for the web page. So if I had to summarize how CCSP works, using a slogan, I will say that our proposal is built on dynamic whitelists, which are assembled dynamically by interacting with content providers. We actually know their needs and dependencies, but at the same time, we don't want to full sacrifice security to these content providers. Let's consider an example which I used to explain the challenges of CSP and how we address these challenges in our proposal. So in this example, we have a web page at p.com, which loads a JavaScript file from a.com. And the JavaScript file in turn has 2 dependencies, because it needs to load another script from b.com and an image from c.com. Now we discuss how this example is supported in CSP and how it's supported in CCSP. Let's start by discussing the traditional approach, which is the one you can use using CSP 1 or CSP level 2. And the core idea in this approach is that one has to whitelist exactly in the page policy all the dependencies of the scripts which are loaded inside the page. So since in this particular example, we have to load one script from a.com, and this script has to load another script from b.com and an image from c.com, I have to include all this stuff into my policy, as you can see in this slide. What is the problem with this form of policy specification? The obvious problem is that script dependencies may be difficult to detect. But if you want to support them, you have to carefully detect them using this approach. And the second point, which is annoying, is that the policy you end up producing is brittle and potentially hard to maintain, because any change into the script I retrieve from a.com calls for a different, for a similar adaptation of the policy which is inside my own page. So I have to change my policy to account for something which is not under my control anymore. So you may argue that this is good from security because I have full control on what the page is doing. I'm listing everything. But unfortunately, previous analysis in the wild showed that this is not the case because developers have trouble configuring this thing correctly, and so they waitlist too much, and they open the room for attacks. To address this issue, there is this recent proposal which is called colloquially strict CSP, which is supported by the latest version of the standard. And the core idea is that essentially we're not using whitelist for script inclusion anymore because this is insecure, but rather we use nonces. So as you can see in this example, assume I want to load the script stat.js from a.com. What I can do is binding a nonce, which is a random value, randomly generated value, to the script tag which loads the script. And then I can update the policy to specify exactly that only a script with that nonce value is allowed to be executed by my own page. What's the problem with this? The problem is that if I only rely on nonces, I'm going to break any script which is dynamically loaded into the page because they don't have any static nonce bound to them. And so, to support this use case, there is this strict dynamic keyword, which essentially tells you that all the scripts which are loaded by a script with a valid nonce are also trusted to be executed. So in particular, as you can see in this case, I don't need to specify the dependency from b.com anymore, because this script is recursively loaded by a script with a valid nonce, so the strict dynamic is perfectly fine for this. But still I have to list the dependency for the image. So I must still include in my policy that the script may load some image from c.com. What can we say about this policy specification style? Well, first of all, this policy specification style improves protection against script injection. Because since I'm binding nonces to specific tags, what I'm doing is that I'm really closing the door for a malicious script. I'm identifying script very precisely, which is good. And at the same time, since I'm relying on strict dynamic, I'm also improving robustness to code changes in script. Because now if my script needs to load some other content from other origins, I don't need to adapt my policy anymore, which is good. But as you can see, there are also a number of criticisms to this approach. And the first point, I already mentioned it, is that the mechanism has only a limited scope because it only supports scripts. In the previous example, if you recall, we had this dependency from c.com, which is an image, and still I have to whitelist the dependency explicitly inside my policy. So this is not a full solution to the problem of script dependencies. Then we have a problem of poor granularity, because the script dynamics keyword provides an all or nothing relaxation mechanism. Because the point is that now any script which is in the page is allowed to recursively load other scripts. So essentially everyone can relax the policy arbitrarily as he likes. And so this is not supporting essentially the principle of least privilege. I don't have a fine-grained policy relaxation anymore. And the last criticism is that nonces can be bypassed, as shown by very recent works, because they are still included inside the DOM of the page, which is notoriously hard to protect. And they complicate the security auditing because we have to check essentially both the policy and the HTML to understand what's going on inside our own pages. Okay? So now I'm going to tell you a little bit more on how CCSP works and how it addresses this shortcoming. And the idea essentially is that we propose a paradigm change where the policy is assembled dynamically by interaction with the content providers. So in this specific case, the developer of p.com only writes an initial content security policy, which accounts for the direct dependencies of the page, and it provides, as I mentioned, some upper bounds for policy relaxation. And the developer of a.com, in turn, provides its own content security policy, which only whitelists the script dependencies. So concretely, we can have a look at how the two policies look like. So in the policy of p.com, you can see the use of two different headers. We have the CSP compose header, which essentially tells you what is the initial content security policy of the page. As you can see, the policy here is very, very simple, because initially I only have to load something from a.com, and in particular a script, which is called stat.js, and nothing more. And this is what is whitelisted by the initial policy of the page. The second header, which is called CSP intersect, is the header which provides the upper bound for policy relaxation. And in particular, you can see that these upper bounds have a scope, because I can define that the script which I load from a.com, and which is called stat.js, can relax my policy to whitelist some additional scripts which must be loaded over HTTPS. So I don't allow the inclusion of scripts over HTTP in this specific case. And the script is also entitled to get images from every place on the web, however it likes, using HTTP or HTTPS, but no other relaxation is possible by part of the script. The policy by a.com, as anticipated, includes only the dependency of the script which is retrieved by a.com. So in this case, if you recall, the script needs to load one other script from b.com, which is called dep.js. And then the script needs to load some other images from c.com, which are not whitelisted precisely. And what we do, we just whitelist the full origin, okay? What happens at runtime in the browser is that all this information is combined, so that the policy which is enforced at p.com is dynamically updated to be relaxed from the initial policy into this other policy, which is built by composition. How is it built? The idea is that we start from the initial policy, which is expressed in the CSP compose header. And what we do is that we extend with the dependencies specified by a.com. And both these relaxations are possible because they comply with the upper bound, which were specified by the developer of p.com. In particular, the script can be loaded because it is loaded over HTTPS, as enforced by the CSP intersect header. And the image can be loaded because the CSP intersect header tells me that I can load images from every place on the net. And nothing more can be loaded by the policy. So as you can see, these policies are assembled dynamically by interaction with content providers. What are the benefits of the approach? The first benefit is that the mechanism we propose has a realistic support for fine-grained whitelist. Whitelists were first proposed in CSP at the very beginning, but we argue that it is not easy to support fine-grained whitelist in CSP, as shown by empirical evidence on the field. And instead, with this collaborative effort, it is possible to be very fine-grained, because essentially every component in our scenario has only to account for the direct dependencies, which are much easier to identify than the indirect ones. The second benefit of the approach is that we have a very general mechanism for policy relaxation. So strict dynamic is something which is useful, it's nice, but it is still limited to script dependencies. While with this approach, you can essentially relax policies to account for any kind of dependencies which are needed by your own scripts. And in particular, this allows you to support nicely HTTP redirects and or advertisement, which typically loads also other stuff. And the last benefit is that since we have this scope information inside the CSP intersect header, what you end up having is that the principle of least privilege can be applied to policy relaxation, because I can specify different upper bound for policy relaxation for different scripts. What are the main drawbacks? One point, of course, is that we're proposing a paradigm change, because this approach requires collaboration with content providers. But we argue in the paper that content providers often have interest in collaborating on this, because they want their content to be included correctly by websites, because they typically have an economic revenue in ensuring that their contents are loaded correctly, right? And the other point is that indeed we are increasing the complexity of the design, which is normal when you really want to improve expressiveness, in particular for debugging, because now the policy which is enforced in the page is not a static policy anymore, but it's a policy which is assembled at runtime and may be harder to debug. In the paper, you can see an evaluation of 3 different aspects of CCSP. I don't have time to go in full detail here, but I want to mention some points. So we have a security analysis, where essentially we analyze CCSP with honest content providers in mind, which is essentially the same threat model as the CSP, because if the providers are malicious, also CSP does not provide good security guarantees. And we show that developers have the last word on security, thanks to the upper bound policy relaxation mechanism we propose, which looks pretty obvious, but in fact the enforcement model is not so straightforward as I mentioned. You can check the paper to understand what I mean. And other aspects we evaluate are the backward compatibility and deployment cost. So we designed CCSP to be backward compatible because it is built on top of new HTTP headers, which will be ignored by legacy browsers. So this is not going to break legacy browsers. And the interaction with the content provider never makes the initial content security policy tighter. It can only relax the policy, which is very important because in general, different content providers may be included in the same page. They may not be aware of the presence of each other, and so they may break stuff if they put unduly restriction on the other content, right? So this is important to ensure a smooth deployment of this. The deployment cost looks reasonable because we were able to implement CCSP using CSP as a black box, because indeed the policy specification style does not change, so you can really reuse the existing implementation. You only need a way to relax policy dynamically, but there is no major change in implementation. And also for web developers, we think it's a nice proposal because there is no major changes in the design philosophy with respect to CSP, but actually we only need to focus on direct dependencies, which are much easier to identify than indirect ones. We collected some evidence on the field that CCSP can be useful by analyzing CSP violations in the wild. So we built a crawler where essentially we navigate some top websites of Alexa and we collect violation of CSP policies. And we focus in particular on two classes of violation which are hard to fix in CSP. The first class of violation includes dependencies, and the second class of violation includes HTTP redirects. So I already told you that dependencies are hard to accommodate because they need to be identified precisely and whitelisted in the policies. HTTP redirects are also annoying to deal with because every time something is relocated, you have to put the new location of the content you're loading inside your own content security policy. So you can see on the table on the right that there is a breakdown of the violation due to script dependencies depending on the loaded content types. And you can see that 96 of these violations are due to scripts which load other scripts, and these are cases of dependencies which are nicely supported by strict dynamic. But we also have a number of other cases like fonts, frames, images, etc., which are not supported by strict dynamics, and this must be explicitly whitelisted in the policy, which is something we naturally capture using CCSP. As to HTTP redirects, there is no support for this into CSP level 3. And again, you can find there is a bunch of these violations in the wild, and these violations are difficult to fix in CSP, but not in our proposal. We also managed to implement CCSP as a Google Chrome extension, and we tested it on some real websites. In particular, we used our prototype to fix some CSP violations at twitter.com and orange.sk, which were in particular the one about Orange.sk. I think it's interesting because it's an example of redirects, which actually depends on the language of the browser which is used to access the page. Depending on the language of the browser, you get redirected a different variant of Google specifically, and only the google.sk was whitelisted by developers, so it was not rendered correctly in our browsers. Instead, using CCSP, we are able to fix this violation very nicely. We also performed a preliminary assessment of what is the deployment cost of CCSP for the most popular script providers. You can see on the table on the right that for the most popular script provider, the number of scripts which are loaded from them is relatively small. So these providers do not need to write many different policies. The number of policies they need to write is limited. And also the policies they need to write are quite simple, because most of the violations are limited to a single content type, and they're also fairly limited in number. So these scripts do not seem to have very difficult policies to write. And only by writing policies for these scripts, we're providing benefits to a large fraction of the web, because these are the most popular providers in the wild. This is just a summary on how CSP is evolving. So when moving from CSP1 to CSP2, what we got is the support for whitelisting individual inline script. We solved the first challenge, which I mentioned at the beginning of my talk. When moving to CSP level 3, We got some mechanisms to simplify recursive script inclusion and to improve policy specification thanks to the use of a strict dynamic. And finally, I include in this slide also our proposal, CCSP, which has a more general mechanism for dynamic policy relaxation, which is still based on whitelist. So we move back to the initial design philosophy of CSP. To conclude, CSP is facing some significant deployment challenges in the wild, and the evolution of CSP is trying to address these challenges. We propose the first extension of CSP, which is called CCSP, and supports the dynamic nature of common web content, including advertisement and HTTP redirect. We designed our proposal to make it secure, backward compatible, and easy to deploy. But our proposal calls for a paradigm change with respect to traditional CSP, which is something you may like or not. But I think that an important message here is that our proposal is an academic proposal. This is not a W3C standard. But the problem it tries to address are problems which are still unsolved by CSP. And I really think that addressing these issues is very important for the success of the standard in the next future. So thanks for your attention. If you're interested in our work, you can check that address for finding our reasoning of this. And you can also write us at that email address. Thank you.
Yeah, Ben Stock from CISPA. Thanks for the interesting talk. I was wondering, as a developer, you said you have kind of control over the resources that are then, well, included, for example, images. But is it actually realistic that as a developer you know what your content provider will deliver you? So thinking about advertisement, you have real-time bidding, so maybe even when you load the script, maybe even the content provider doesn't yet know what advertisement will be shown. So I'm wondering if, as a developer, I can actually specify something that is more restrictive than, I don't know, HTTPS star.
Okay, that's a good point. So in many cases, we think that content providers know when they supply the script what is the policy which needs to be supplied with the script. This is the case, for example, of the Google use at orange.sk, because every time some script from Google is loaded, it knows in particular, it can know in particular which is the top-level domain which needs to be whitelisted in the specific case. Mm-hmm. Of course, there may be cases where the actual script dependencies can only be determined at the client side. If this is the case, of course, the mechanism does not work. But as long as the dependencies can be identified precisely at the server side, you are able to accommodate them using this technique. Notice that anyway, all the dependencies in CSP must be accounted for statically already. So be them at the client side or the server side. With our mechanism, you can account for very nicely the case of server-side dependencies, while everything which is computed at the client side may be harder to accommodate. That's also true.
And the other question was, so one of the problems that you mentioned for strict dynamic is obviously that it only, considers scripts. But if you extended that, let's say in level 4 of CSP, they go ahead and say strict dynamic is something that if an image is dynamically generated by included JavaScript, then it's also fine. Would that kind of not bring it to a similar level that you provide here?
So it is possible, of course. So you can devise some new keyword which allows you to propagate dependencies. You can do it. Still, some of the problems we notice are not solved by this. In particular, you don't have any fine-grained control on the policy relaxation mechanism. Mm-hmm. And the other point is that you're losing control as a developer, because everything which is, you have a mechanism basically to whitelist everything which is recursively loaded, but you cannot put a policy upper bound. So we think that overall the design we propose is nicer, even if we understand that for backward compatibility, if you really want to, let's say, address these challenges, you may also try to address them by having, let's say, smaller tweaks to CSP as the one you suggest.
All right, thank you.
Thank you.
Hi, just curious about Bill Aiello, UBC. Just curious about transitivity of trust, your sort of the depth. Your example just has kind of one level, P trusts A, any of the scripts that A trusts. Is that just your policy only allows for one level, arbitrary levels? No. Can my relaxation from the originating domain restrict the depth?
No, so the proposal is totally general. So it applies also for more steps of recursive content inclusion. And the mechanism is designed so that if I put some policy relaxation bound on some script from a.com, and this script loads another script, the same relaxation bound which I put on the original script are propagated to the other component. So that you cannot, for instance, let's say, escape the relaxation bound by loading other stuff from other web origins. And this is exactly one of the points in our security analysis when I mentioned that the real enforcement is slightly more complicated than this, what I show in the slide, and so it requires a more careful security analysis.
Okay,
but
thanks.
it's general mechanism.
So, thank the speaker again.